we've already had spring break, but there's an easy money maker you can always make, and that is that you bet people that you just tell people you're a mind reader. I am a mind reader, okay? And you can bet and play with people and, bet them $100 or whatever, that you can read their mind. You're my guinea pig, okay? Okay, now what you do is you just say, hey, when you were 2 years old, you were shorter than you are now. Am I right? Now, already, how would I know? Because I didn't grow up near you, did I? No. There's no way I would know. The reason I'm calling on her is because she's chewing the pizza. Whatever. What is that? Oh, gum. Chewing gum. Okay, well, then you can talk. But that by itself, that's not what it is. So you go further. And you say, well, I didn't know you when you were a little bit older either, did I? The answer is no. When you were 10 years old, you were taller than when you were 2, but still shorter than you are now. Now, see, that's 2 for 2. You're impressed, right? Yeah. She's not all the way impressed. She's not into this as you're worth that $100. I'll give it to you. So you go to the third part. After you were 10, you started to grow, and you kept on growing until you were about 17, maybe 18, and you haven't grown any taller since. Am I right? I am right. Yes. Okay, now that's what gets you $100, and you can pay me after class. Yeah. But here's the deal. It's a trick. I know you're just, what? It's a trick? All you need to know is how long bones grow. The way long bones grow, when you're a small child, you start off with a bone. This is the shape of one of your leg bones, for example, and it's made of cartilage. And think of it as a cartilage mold. Okay, sort of the shape that the long bone will have, but it's kind of a mold for what you're going to do. And then put parts of this. You're going to have bone on the top part here. So this is going to be bone. And you're going to have some bone on the middle part here. And you have bone on this bottom part here. Okay? Which means you have 2 areas, this area and that area, that has nothing but cartilage. This is known, these 2 areas are known as your epiphyseal plates. And when the bones grow taller, when you grow taller, what's happening here is the elongation, the lengthening occurs at the 2 epiphyseal plates, at the top and at the bottom. And so if we're going to grow, we just let these parts here, the epiphyseal plates grow, and now we can get a longer bone, like so. We still have this overlaying part with bone, overlaying part with bone, and the overlaying part with bone down at the bottom.
So,
yes,
just to clarify the diagram, the empty white space area, that's cartilage.
That's cartilage.
And the squigglies are bone.
Yeah.
That's currently growing.
Yeah, and actually, if you wanted to do it right, you do it like that.
Understood.
But I don't have that young woman there, you, up here drawing my drawings, because she can do it anatomically accurate. Okay? Now, what is happening here is the bone continues to grow downwards like this, and grow upwards from this way, like that. And this bone grows both up and down. And so as your bones are getting longer and longer and longer, this bone keeps going like this, and eventually the bone from the bottom will meet the bone from the top, and now the long bone is completely overlain with bone, and at that point, long growth stops. And whatever height you had is the height you're going to be. Okay? So when the epiphyseal plates get overlain with bone, your growth stops. It takes in humans about 17 or 18 years, which is how I knew that she got to be 17 or 18 years old, and that's when she stopped. And so it's a dirty trick pull on you, I know, but you said you'd still pay me the $100. So that's only fair, right? She thinks it's serious. Oh my God, I don't have 100. She's counting up in her wallet there. 6, 7, 8. Okay, so we've got that. Since a number of you are pre-med types, sometimes you come into patients that one leg is shorter than the other, and one of the things they actually do is they'll go in and they'll actually break some of the bone there, exposing the epiphyseal plates, and the leg will grow a little bit longer. However, see this young woman here? Or even better, you. Stand up. Okay? What if she wanted to be the female basketball star? You know, somebody 7 feet tall. How tall are you now? Okay, she's in the 5s. She wanted to be up to 7 because you want to be a tall basketball player. Could we do, thank you.
No.
Could we just continue at an early age, breaking her bones, and that way you would grow taller and taller and taller? Who says no? Why? Yeah, oh, you would have to break it many, many times. Every 6 weeks you would break it. Wow. What? You're going to pay for it.
Okay.
I mean,
All right,
when she becomes a professional basketball star, oh, she'll be able to pay us all. Okay? Why would that not work? You know why that would not work? If she has to break her leg and grow both legs every 6 weeks, how much practicing can she do? None. So how good is she going to get? She's not. That's why I don't say that. Except for that, they're going to be the 100. Okay. All right. The other part of that chapter has to do with muscles. And I'm just going to do the shortest little bit on muscles to basically say we have 3 different types of muscles. I've got some pictures of these. One of the types is the type that actually connects to our skeleton and helps us to move around. These are called skeletal muscles. Is that a good name for them? But sometimes they're also called striated muscles. Exactly just the same name, striated muscles. Attached to your skeleton allows you to grow, to move. Okay? Now there's a real nice advantage to those kind of muscles. They're strong. So we can just say here they have strong contractions. But they do have a downside. And that downside, you would already know that if you're carrying a heavy weight over your head, you're think about carrying a big old 100-pound weight over your head. What would happen to your arms? They'd get tired. And that's exactly the downside to skeletal or striated muscles. They fatigue easily. That's what it means to get tired. Okay? They're called striated muscles because if you looked at it in a microscope, they have these fine striations in them. Just like that, and it's involved in the muscle contraction, but that's what they look like. I think I actually do have a picture of these. Let me show you. There we are. Oh, there's also a whole bunch of nuclei in here, so we say multinucleate. There. So there's a striated muscle. When you look at it under a microscope, the little bands that you see, it's just so obvious. What are you looking at? Oh, that's striated muscle, because I can see the striations in it. Okay? Let's see, I think I have another. There's another picture of it. I don't know. Looks pretty obvious, doesn't it? Striations. Yeah, I see striations. So there we have it. Okay, the second type of muscle is associated with all of your inside, okay, your innards. This is your stomach, your intestine, the muscles that move the blood through your bloodstream. This is called smooth muscle. And when you look at smooth muscle, man, it just looks boring. It just looks like that, sort of. It's just milky whitish when you see it in the preps. Doesn't have much in it. But now, think about this. How much strength does it take to just go back and forth through your stomach? It doesn't take a lot of strength. Or the muscles associated with the pupil. If somebody shines a light in your eye, how much muscle does it take to close the opening to the eye? Not very much. Okay? So these are not as strong. But the nice thing is they don't fatigue. They don't get tired. They don't fatigue. Okay? I hope I have a picture of these. Yeah, I do. Okay. Well, they have only one nucleus, but I wasn't going to even put that in there. Just like that. Okay? So you look at those and under a microscope. I don't know if they're going to show you those in lab, but if you ever see one of those, to me they always look boring. That's just, yeah, that's smooth muscle. Nothing. But then I didn't want to be a physician, so those are either one. And that leaves us with the third type. And this is called cardiac muscle. And now think of the problem with the heart. The heart is going to take a muscle that's going to pump blood. The guy in the blue, you wrecked. How far does the blood have to go in your body? Yeah. It's got to go through the whole thing. So you're going to need a pretty good muscle to get it there. Exactly. So you're going to need some muscle that has strong contractions. Well, we have one that has strong contractions. That's skeletal muscle. But it has a downside. It gets tired. How would you like it if you're just walking along and, oh, you got those strong contractions in your heart, and your heart just says, well, now I got to rest for a while. Yeah. What do you call someone whose heart has to rest like that?
Dead.
So there's, he said it. Dead. Yeah, dead. Okay. So skeletal muscle will not do. So what we do have is a type of muscle called cardiac muscle that not only has strong contractions, but doesn't fatigue easily. Sort of the best of all worlds. I mean, what a great muscle. Here you could use your muscles all day long and not get tired. Wouldn't you love that? Yeah, we all would, but we don't have that except in one place, the heart. Do you know why? Because why? I don't know. Help her out. Why is that the only place we have? I mean, think about this. If we had this attached to our skeletons, we could run all day long and not get tired. You could run a marathon, and at the end of the marathon, run again.
Energy required to maintain those muscles?
The what?
Is it because there's a lot of required energy to maintain those muscles?
Aha, exactly right. The amount of energy it takes to work these muscles is huge. A lot of our energy goes into getting these to work. We don't have enough energy to do it in our skeleton as well. We have only enough energy to do it in one place, the heart, and that's why we have it there. Okay.
So when somebody goes into cardiac arrest, does it run out of energy? Does it just
No, that's different. We're not going to get into that, but I could. But let's look at how they look. If you look at how the heart works, the heart has to pump as a unit. Okay, it's got to pump all at the same time. And so what we have is individual muscle fibers are sort of woven. So I'm going to try to make this look woven. I'm not doing a real good job. Like a basket. Think basket up there. So if you can draw a basket for me, draw a basket. You have a basket. And that way the whole heart could contract as a unit. But, and I'm not going to go into this, but we might later. In order for a muscle to work, there has to be a small electrical event prior to the muscle contracting. So there's a little charge to it, and then the muscle contracts. Heart muscle has a number of these, what are called intercalated discs. I'll write that down for you. intercalated discs that help transmit the electrical charge across the entire surface of the muscle of the heart, and that way the heart contracts as a unit. So if you get charge and it spreads across the whole thing, then the heart will contract. You have to have the electricity, then the contraction, and these intercalated discs help spread that charge of electricity so the heart contracts just as a unit. Okay, so there we have that. We can put in lots of, I don't have it there, but your picture will show that. Lots of nuclei in this one too, multinucleate. Just like so. I hope I have a picture. Yeah, there's a little cartoon sort of thing. We have all the right words in it. And you can't really see that it's woven in there, but it really is. I don't know. Can you see it? Does it look woven to you?
It's not really.
Not really, but it is. It's like a basket. Trust me on that one. Okay, so now somebody has, well, a whole bunch of you have asked, where's the material going to end for the first test? This is where it's going to end, right there. So draw a line across your page, and that's the end of the material for the third test. Okay, we're going to go on. Okay, I was going to give it away. Okay, the next chapter that we have that we're going to start, and I'm just going to start it just a littlest bit here. I'm going to give it away. I don't want to. You're going to give it away?
Yeah, you can give it away.
Does anyone want a piece of pizza? It's a sausage pizza, I think. It's free. It's courtesy of the Pre-Med Club. They love us to death because we're always very good at getting rid of their pizza. Which is nice. The next chapter we're going to start is called homeostasis. And it's a pretty big chapter in your book, and I always kind of wonder why that is, because it seems to be pretty simple. Homeostasis comes from two Latin words. One is homeo and one is stasis, and this means the same, and this means to stay. To stay the same is what that translates to. To stay the same, and you can make a formal definition that homeostasis is all of the mechanisms in the body to keep you the same. We can probably make it fancier, but that gets it done. Okay, so now let's see what I mean by that. Okay, the gentleman way up there who's on his phone. Dude, you, red, yeah. We're going to do an experiment with you. So you might want to pay attention just for a second. Okay? Here's a pot of boiling water. Got it? Here's, by the way, do you know what human body temperature is? Well, hope not. 98.6. We'll pretend you said that. Okay? 98.6 Fahrenheit, or you might think of it in terms of Celsius, which is what we're really supposed to use, but no, we're Americans and we don't do that, do we? Okay. But the gentleman up there, we're going to put you in this pot of boiling water and run your temperature up to just under boiling, 210 degrees Fahrenheit. You got the scenario. That's you in this boiling, almost boiling water. What's going to happen to you? Say it loud. It's a 3-letter word. Burn is 4 letters. Would you like to buy a vowel? You will die, yes. Thank you. Good. Excellent. Wonderful. I mean, not wonderful for you, but that's what we're going to do to you. We're going to boil you, and you will die. What we're demonstrating is if you don't stay the same, you die. Let's try another one. That was kind of mean. I'm going to say it was the class that did that to you, not me. If it was me, I would put you in this freezer. This freezer at minus 20 degrees. 20 degrees below zero. And lock the door. You're the one that put him in the hot water. I'm putting him in the freezer. What would happen to you? 3-letter word. You would die. Yes. In other words, if you don't stay the same, you die. That's homeostasis. If you don't stay the same, you die. That seems pretty simple, right? Yeah, that's such an easy concept. Why your book spent like 75 pages on it, I do not know. Because it's just so simple. Let's do something else, though. I need to give you one of my laws. I think this is like a third law. My third law is pretty simple. What goes in must come out. What goes in must come out. See that water jug there? That's a gallon jug. Hold it up so the class can see. But it's only half full. It's just got half a gallon there. Got it? Okay. Did you see it? Did you see this water jug? Okay. We're going to make you drink that water jug. All half gallon of it. Half gallon. There's only 2 L's in gallon, not 3. Half gallon of water. Okay? And we're going to watch her as she drinks. Is it okay if she drinks your water? No? Okay, well, we'll beat you up and then you feed her the water anyway. We're going to make you drink that water, half a gallon. How much are you going to pee out? Half a gallon. Now, why do you know that's right? Because what goes in must come out. Now, think of why that has to be. If she didn't pee out a half a gallon of water, over time she would be adding more and more water to her system and her bloodstream, and her blood would get too liquidy, and there's not enough salts to water balance, and what would happen to you then? You would die. Exactly. Pardon? Did anyone see any movies over the break? What'd you see?
Knight of Cups.
Knight of who?
Cups. It's a Terrence Malick movie.
Knight of Cups. Has anyone else seen that? Is it any good?
It's pretty good, yeah.
It's pretty good. Okay. Did you see a movie? What did you see?
I went to go see Zootopia, that new cartoon
Utopia.
from Disney.
That's a cartoon, isn't it?
It was, yeah, I went on a date.
Oh, he went on a date, so he went.
She
What'd you see?
I saw it too.
Oh, do you like it?
It was damn good. I will stand.
It
by
was
that.
damn
It was
good.
a good movie. It
Okay.
wasn't just a kids movie.
Well, remember, one of my favorite movies was Finding Nemo, and that's not a kid's movie either.
Was the bunny cop movie?
Yes, it's the Bunny Cop movie.
Bunny cop?
Bunny cop.
A bunny cop.
I had a bootleg copy of this.
I gotta go to more movies. But the movie I went to, they had the popcorn, and they have a salt shake. You ever seen that? It's not seasoning, it's salt. I mean, it says seasoning, but it's salt. I tried it. I stuck some in my hand and tasted it. Oh, that's salt. Okay, so you go to your movie theater, you get that garbage can size of popcorn.
Garbage can size.
You see, now you know what I'm talking about. You know what I'm talking about? Yeah. And you put in it
Butter.
a whole tablespoon of salt. Whether it says seasoned salt or whatever. That's what you just put in. How much salt are you going to pee out? A tablespoon, and you know that's true why? Must come out. Exactly. Edwards' third law. It's good. Because if it didn't happen that way, if you retained that salt, then you'd get more and more salt buildup in your bloodstream, and eventually what would happen to you? You would die. Or if you peed out more than a tablespoon of salt, then all of a sudden now you don't have enough, and you would die. So yeah, all of this has to do with homeostasis, how to keep the body the same. Okay? Because if you don't, you die. So many different ways to die. Okay, now we were talking about temperature here. Let me get rid of this part here. I just want to do a little bit. But back in about second grade, I think, they talked about some animals were warm-blooded, some were cold-blooded. And I can't really remember what grade it was that we learned that, but I know we did learn it at one of these grades. Do you remember those? Do you remember which animals were warm-blooded? Mammals, yes. What else? Anything else? Well, reptiles aren't one of the ones in the mammals, okay. What's the other one? Birds. See, he was there that day. You must have missed that day. Yeah, basically we were all taught birds and mammals are warm-blooded and everything else, all the rest. That's a nice way to say that. Is that what, gentlemen there, is that what you learned? Do you remember what grade that was that we did that? 11th grade. Oh, he was a slow learner. Remember what grade that was? 7th grade.
Maybe.
Really? No, that was elementary school. Wasn't it elementary? 3rd grade. 4th grade. He didn't get it until 11th grade. But at least you got it. That's important. At least you got it. Now, here's my question. How many of you did not grow up in Texas? Did not grow up in Texas? Where did you grow up? Nuevo Leon, like Monterrey?
Oh, cool. Yeah.
Okay. What?
You know, that's so cool.
I work with a dude who lives there. The university. You're not excused from what I'm saying. Where'd you grow up?
Chicago.
Chicago, he would be excused. Anyone else? Where'd you grow up? You're not excused. You're basically Texan. We're all together. We're all together in this. Okay, so unless you were way up north like Chicago or somewhere in Michigan, Illinois, Wisconsin, you would be excused. But if you grew up in Texas, then you know exactly what I'm talking about. We would go to school during the school year, and then summer comes, and as little kids, what did we do? What did you do in the summer? When you're like elementary school age, day to day. Play! You'd go outside and play. That's what we did. We went outside and played. We'd go up and we'd catch a lizard and we'd pull its tail off. Wow. What do you mean, wow?
For research purposes, I'm guessing?
Elementary school kids. Didn't you ever do that?
Perhaps. Yeah.
I know you, look, I know you did. Watch this, watch this. How many of you, when you were little kids, pulled off the tail of a lizard? You knew that it grew back, so you take a look to see that we are not the weird ones. He's the weird one.
Okay, I'm sorry.
Okay? Yeah, we would, but you never did. Yeah.
Maybe.
Yeah, we would catch the lizard and pull their tails up, and then they'd wiggle for a little while. They were a lot of fun. And we learned a little bit about herpetology, how lizards work, because we learned that they can regenerate their tail, and that this is used for getting away from predators, and we were acting as a predator. So, yeah, what a wonderful little lesson, and what a fun thing to do if you're a little kid. Play outdoors. And remember, we went to second grade or third grade, and we were told that the warm-blooded mammals, warm-blooded birds, and we knew we were one of those mammals, so here we have that 98.6 Fahrenheit, and that set in our mind that that's warm-blooded. And we're outside in Texas in the summer, and how warm does it get here? 103, 105. Yeah. And we were taught that all the rest, they take their temperature, whatever it is outdoors, that's what their temperature is. Okay, so here we are playing with these lizards on a hot summer's day, 105 degrees, and we can think that that lizard's temperature is 105. And then we get to our school, and the teacher's telling us that mammals are warm-blooded. You are warm-blooded, but the lizard is cold-blooded. And you're thinking to yourself, wait a second, 105 degrees is cold-blooded if 98.6 is warm-blooded? What? Did you one time stand up to your teacher and say, hey, teach, you idiot, what do you think we are, stupid? You didn't do that. Did you do that? No. I know, I didn't either. I kick myself to this day. Why didn't I do that? The teacher is an idiot. And I heard a golden opportunity. Teach, you idiot. Thinking we're stupid or something. Only thing I've come up with is back then we were real short and small. And the teacher seemed huge. And we thought that she might squish us or something. You didn't do it either, did you? But you had a perfect opportunity to. You could have. Now, growing up in Michigan or Illinois or wherever, Chicago, didn't have that opportunity because it never got that warm, okay? Now, the problem that we have here is looking at all that rest. The way that we generate heat is we do it internally through exercise, things like that. Moving our muscles generates heat. Now, let's think about a couple things here. Charlie the tuna. Okay. How many of you have never heard of Charlie the tuna? Okay, now that's a generational thing. Ask your parents if they've ever heard of Charlie the tuna. Charlie, who has heard of Charlie? What is he the spokesman of?
He's for like some tuna campground.
Yeah, do you remember which one?
Starkist,
yeah, Starkist tuna. He was the one they always put on the labels. He's coming back. So if you if your hand was up that you never heard of him, you got to watch more television because he's back. How many of you eat tuna? Oh, a bunch. You eat tuna, okay? What do you know about tuna? Tuna fish. The young woman there. Where do they live? I'll start easy. Where? Wait. I've got to make a point. Here's the map of the world. It's not a very good map. We'll soon. Ooh, I'm really messing up here.
It's not the worst of it. See?
I forgot. Here's Hawaii way over here. We'll have Australia. I forgot Europe. I forgot Africa. I'm not doing good. I guess we'll have it over there. Map of the world. Do we have tunas in our Gulf of Mexico? She says, no, you're wrong. We do. Remember, she said she eats tuna, so she should know. What about on our field trip to Hawaii? Could we find tunas living there? Yes, she says, yes, excellent. Yes. And in fact, if we then went over to Australia and checked out the Great Barrier Reef, would we find tunas there? Yes. So we've got tunas here. How about the Atlantic Ocean? Would we find tunas there? Yes. Oh, see, now you know a lot more about tunas than you thought. Here's going to be a hard one. What about off the coast of Alaska or the North Sea up here where it's really cold, near Iceland? Would we find tunas there? Yes, excellent. In other words, if it's ocean, we got tuna. Now, when we watch television, a few times we watch television, apparently. You guys, you don't watch television. You watch the animals. And they always tell us the fastest animal is who? The cheetah. Boy, how fast is cheetah? How fast is cheetah? 60 miles an hour. She says, damn, that's fast. 60 miles an hour. Okay? Now, next time you get to watch the cheetah go 60 miles an hour, watch how far it runs. It can run from about this wall over here to about here. And then it gets tired. It's a sprinter. I mean a short sprinter. It can go at that length. Okay, now, another thing we didn't talk about on muscles, but if anybody's ever done track, does anybody ever run track? Okay. Did you have to warm up before you ran? And in a meet, was it important to warm up first? Did they ever tell you why? Because you could pull a muscle if you didn't. And did you ever try to run if you weren't warmed up? You ever tried it? You are much slower. Much, much slower. Yeah, and that's because a warm muscle contracts with greater force. Okay? And so that's why they want you to warm up before a race, is that a warm muscle contracts with more force, you can get faster times. Which anyone who, if you don't believe it, just go out and run and time yourself and then warm up and then try it again and it will be faster. Okay? Charlie the tuna can swim 60 miles an hour, but it can do it for a 24-hour period. That's far better than the cheetah. Far better. Now the question is, if we take Charlie out of here, out of the North Sea, that's 40 degrees centigrade. 40 degrees Fahrenheit. That's pretty chilly water. If you don't believe that, just get some ice cubes in a bathtub and jump in, and you'll see, oh, that's chilly. Okay? 40 degrees. So the question is, how can this fish go 60 miles an hour, 24 hours a day at that kind of temperature, if he's all the rest and his body is that temperature? And the answer is, Charlie's not that temperature. Charlie generates heat internally just like we do. And so if you actually measure Charlie's temperature at 40 degrees C, his is going to be a little over 75 degrees. Quite a bit warmer than the ocean temperature, which means that we can't put just birds and mammals over here. We're going to have to put Charlie over here too, Charlie the tuna. What about this dude? Let's see if I can draw it. I don't think I can, but you'll see. We'll see if that's correct. It's another fish. Thank you. Good. Okay. I know. Jaws. There we got Jaws. Where do Jaws live? Tell me. The ocean. Do they live all the different areas that tunas live? He says no. You know what they like to eat? They like to eat Charlotte, tuna. Then they live in all the oceans. Yeah, and that's where we find sharks all over the oceans. And again, we'll go to this North Sea, 40 degrees Fahrenheit. We take the shark's temperature, and by the way, they do not take it orally. They don't stick a thermometer in like that to a shark. You know, can you imagine here? Oh, yeah, no, I don't think so. They take it in this way. And if you were to measure his temperature, you would find it is not 40 degrees C. It's closer to 50 degrees. And the way they do that is the shark generates heat internally, just the same way we do, which means now we better put Jaws over here too. Now some of you may say, hey Edwards, enough about fish. Is that it? No. We live here in the Rio Grande Valley. We're home to a lot of butterflies. Has anyone ever seen this? Now you have to be up early in the morning to see this, but early in the morning you might see a butterfly and he's got his wings up like this, and then he's just sitting there and then he starts going like this. You've seen that. Do you know what he's doing? Using his muscles. It's too cold in the morning for it to fly. So by warming up its muscles, it gets more strength and he can fly that way. Which means he's generating heat internally. So now we got to add to this list again. Butterflies. You may think, well, that's got to be all of them. But we forgot our friend the cockroach. We can't ever forget our friend the cockroach. There's a cockroach. Say he's in your house, 72 degrees. You take the cockroach's temperature. It's got to be a very small thermometer. That would be 72, and the cockroach's temperature comes out a whopping 74. It's slightly higher, but it is higher. How does he do that? Well, he uses his muscles, generating heat internally the same way we do. So we got to have a cockroach here also. But the bottom line here is these words warm-blooded and cold-blooded that they introduced to us in like 2nd or 3rd grade, they're just not right. That's not correct. That's not what they really mean. So we can get rid of those. What they're really talking about back then, and this is why we didn't get this as the words, well, for one thing, we had 2nd grade teachers. This is generate heat internally. These are the endotherms. And these are the ones that have to take it from the outside. These are the ectotherms. And we probably didn't learn those simply because that's too hard for a 2nd grader to have on their spelling test. Now, you as an 11th grader, that seems that should have been fair game. But the problem there is it doesn't separate out the birds and the mammals from all the rest. And there's something about early on, there was a whole group of people that just thought, we cannot be animals. That would just demean humans. We're not animals. Well, we are animals. And now we recognize that. We're one of the mammals. But they still wanted to have, well, mammals are cool because they're like us, and birds are cute. So we want the fuzzies and the birdies to be a group together. And, you know, slimy old fish, we want them separate, or snakes that have scales, we want them separate too. So they thought, well, what's really happening here is we can maintain a constant body temperature, and birds can maintain a constant body temperature. And the word for constant body temperature is homeotherm, temperature the same. Okay, so we can get rid of these here. And that way you have a constant body temperature, and these other things like Charlie, his temperature still fluctuates, okay? And Jaws, his fluctuates. Now the word there is poikilotherm. Okay, and so a varying temperature, a fluctuating temperature is a poikilotherm, and you can just imagine getting that in second grade as a spelling word. On Friday you will have a test, and you'll get to spell poikilotherm. And you would say, the hell we will. But see, now we have constant temperature. Well, we have a problem with that too, and that is, this is a great exercise to do. When will I do that? Let me see. Let me do it over here. I'll do it right there. That's the place. Do this and this. This. Here's an experiment you can try at home. It really does work. Take your body temperature at different times of the day. Here's 98.6. Okay, so this is body temperature. And take it in the morning when you get up, and then again at noon, then at like 6 p.m., and then again at midnight right before you go to bed. And do it the next day, 6 a.m., noon, 6 p.m., midnight. You can do that for a couple days. It really just takes a couple days to do this. And the first thing you'll find out, let's see if you can talking about you. Early in the morning, right before it's time to wake up. Don't you pull on the yeah. Early in the morning. Early in the morning, chilly. Early in the morning. Oh, that's awesome. Don't you do that early in the morning? Yeah. You know why? Because your body temperature, you're going to sleep all night, your body temperature drops. And that's exactly what you'll find when you measure it. Is that early in the morning when you first wake up, your temperature is not 98.6, it's down there closer to 97. And then if you're a typical college kid, you do the same things that I did when I was a college kid. Got up, got on my jogging outfit, jogged about 5 or 10K, all before breakfast. And you know I'm lying, right? I was a college student. But as you're getting up, you eat your breakfast, you're exercising, your body temperature starts to rise. You go to your classes. How many years did you go to 11th grade? Just one. Okay. Just wondering. But you go to your classes in the day, you eat lunch, and in the afternoon, if you're a typical college student, as soon as this class is over, you go out and you hit the tennis courts. But your temperature continues to rise, going up probably well into 99 plus around dinner time. Then after dinner, and again, a typical college student, after dinner, you get down at your desk, you sit down, you open up your books, and you study for hours and hours and hours. Just typical college student. Okay? And then you go to bed, and while you're sleeping, you're not moving your muscles, you're not generating body heat, and your temperature drops, and it keeps dropping until right before morning the next morning when you're chilly and you pull on the covers and you start it again. And so what we have is, even in our species, we have a fluctuating body temperature. So you're left with, that word really doesn't work either. It doesn't describe to keep birds and mammals separate. Now, if you want to get really famous, it will not make you a single penny, but it will get you fame. If you can come up with words that really describe what's going on in temperature, you get famous. But as it is, you just got to remember that all of those words have problems, and just we'll recognize it that way. Now, the question you should say is, well, how do they come up with this 98.6? Well, you'll notice that twice every day, it is 98.6, and the average over the day would be 98.6. And that's where it comes from. Okay, I'm going to stop right there for today, and then we'll go over what's going to be on the test. So I don't know if we will. Now, you see my extensive notes up here on the table here. I actually did bring my entire notes, which I thought I would share with you guys. That'll help show what's on the test. Now let's see, I gotta go here, and then I hit this. I hope that works. Ah, there we go.
Wow.
Now let me just see here. Focus. There.
Feels so much better.
Okay, here's a complete set of lecture notes. She's taking a picture of it just so she doesn't miss out on anything. You have all this stuff, folks. She has a picture. Now go to the start of your notes. I just happened to see her snapping a picture of this, and I'm wondering, what the hell is she doing that for? We start up there at digestion. Yeah, there we go. On this page. One more page. There we go. And that's where she had a line across her page. It says start the material. So we went through digestion, we went through the anatomy of it, the physiology, how the different parts work. We then looked at a little bit of the food pyramid. Remember the food pyramid? Do you remember what was on the base of that food pyramid that you're supposed to eat the most of? Do you remember what was on the top that you're not supposed to eat that much of? Yeah, fats and sugars. Then we got into, ooh, what do we got? We got digestion. What were we having? No, what was it? Oh, salad. Okay. Well, see, it's getting fiber. That's good. We then got into the different kinds of skin glands, the secretions, and we went through those 3 different ways, if you remember that, the types of secretions, or the anatomy of the secretory cells, or the mode of secretion, merocrine, cholinergic, apocrine, those. Then we got into the circulatory system, and we looked at what the components of blood was, the plasma, the cellular part. Then we got to the tubes. Am I going to have 20% of the questions from each one of those categories? I doubt it, just because I made up the questions that I didn't get. I don't know.